Welcome back. In this lesson, we're looking at one of the most practical data structures in Rust, the vec, short for vector. A vector is a growable heap-allocated list. It's Rust's answer to ArrayList in Java, list in Python, or vector in C++. Where an array, which we met in Lesson 1, has a fixed size baked into its type, a vector can grow and shrink as your program runs. This makes vec the workhorse collection of everyday Rust code. Anywhere you'd reach for a dynamic list in another language, a queue of work to do, a set of results to collect, a buffer you append to as data arrives, you'll reach for ves. Vec is also generic, which means it holds one specific type of element, a vec of U32, a vec of string, a vec of your own custom struct. By the end of this lesson, you'll know how to create vectors, modify them, read from them safely, iterate over them, and even handle the case where you need to store different types in one vector. We'll keep the focus practical. This is probably the collection you'll use most. There are two main ways to create a vector in Rust. The first is vec::new, which gives you an empty vector. It's useful when you're about to build up a vector element by element, or when you need an explicit empty starting point. Because Rust can't always infer the element type of an empty vector, you often need to annotate vec of I32 in this case. The second way is the vec! Macro. This is a literal syntax. You write vec, followed by square brackets containing the initial values, and Rust figures out the type from the contents. It's identical to vec in Rust's broader ecosystem and tools. The vec macro also has a clever form with a semicolon. You write a value, a semicolon, and a count, and you get a vector filled with that many copies of the value. In the example, vec:0.5 gives you a vector of 5 zeros. Use vec::new when starting empty and the vec macro when you have initial values. Both are common and idiomatic. The most common operation on a vector is appending an element to the end with the push method. Push is efficient, usually constant time, with occasional reallocations as the vector grows beyond its capacity. To remove from the end, call pop, which returns an option of the removed value, since the vector might have been empty. Push and pop together turn a vector into a stack, if that's what you need. You can also insert at any index with the insert method, or remove at any index with remove. Both of these are O of n operations because elements after the target have to shift up or down to fill or make space. For small vectors, this cost is trivial. For large ones, it adds up. Prefer push and pop whenever you can. If you need frequent insertion and removal at arbitrary positions, you may be reaching for the wrong data structure. Rust's standard library has vec::dec for efficient two-ended queues and more specialized collections in the wider ecosystem. To read an element from a vector, you have two options, and they trade off in an interesting way. Option 1. Use square bracket indexing, like v'(i). This gives you a reference to the value at that index. It's succinct, it's familiar from almost every other language, but it has a catch. If the index is out of bounds, your program panics. Option 2. Use the .get method, which returns an option. If the index is valid, you get some wrapping a reference to the value. If not, you get none. No panic. You handle the missing case as an ordinary value. Which should you use? Square bracket indexing is the right choice when you're certain the index is valid. Maybe because you just checked the length, or because the index comes from a loop that stays inside bounds. Get is the right choice when the index comes from somewhere you don't fully trust. User input, network data, parsed content, anywhere failure is possible. Rust's philosophy is to be explicit about which case you're in. The language gives you both tools, and the right one depends on your guarantees. Iterating over a vector with a for-in loop is the most common way to work with its contents. There are 3 flavors, and they differ in what kind of access you get to each element. First, for n and v moves each element out of the vector, consuming the vector in the process. You can only do this once. Second, for n in ampersand v, iterates by reference, borrowing each element for reading. The vector is still usable after. Third, for n in &mut_v iterates with mutable references, letting you modify each element in place. With a small wrinkle, you'll need to dereference with a star when assigning. The ampersand forms are what you'll use most of the time. You almost never want to consume a vector just by iterating through it. Beyond for loops, vectors support a huge library of iterator adapters: map to transform, filter to select, collect to gather into a new collection, sum, product, any, all, and dozens more. These chain together into expressive pipelines that generate efficient code. We'll cover iterators in full depth when we get to them later in the series. Every vec holds one type of element. That's a deliberate design choice. It lets the compiler lay out the vector efficiently in memory, and it lets every iteration know exactly what type each element is. But what if you genuinely need to hold multiple different types in one list? A row in a spreadsheet, where each cell might be a number or text or a flag. A parsed language, where expressions can be literals or identifiers or function calls. The answer is to wrap the types in an enum. The enum becomes the vector's element type, a single type from Rust's perspective, but each variant of the enum can carry different data. When you iterate, you match on the variant to recover the underlying value and handle each case accordingly. This pattern, enum wrapping diverse types stored in a vec, is everywhere in real Rust code. You'll see it in parsers, in interpreters, in scene graphs, in IR for compilers. Anywhere a sequence naturally has heterogeneous items, it works seamlessly with everything else we've learned. That's vectors. Create, modify, read, iterate. The everyday workhorse collection in Rust. Next up is one of the most important topics in the language: error handling. That's where we'll put result to real work and see why Rust's approach feels so different. See you there.